Okay, so in lesson 4.3, we're going to talk about logarithmic functions. To talk about logarithmic functions, let's first of all talk about the exponential form and the logarithmic form of an equation that has a power, a base, and a number. So an exponential form of an equation is where you have a base, like 5, you're raising it to a power, like 3, and you get a number, like 125, which is 5 cubed. The logarithmic form is the same information, but it's just put in different places. So this says log base 5 of 125 equals 3. In this form, the base is this little number next to the word log. The number you get is 125, and that goes right next to log base 5. And then the power is on the right side of the equation. So whereas the exponential form is giving you a base raised to a power, and it's asking you, what is that number, 125? On the logarithmic form, you're given the base and the number, and the question is, what exponent do you put on 5 to get 125? And the answer is 3. So in the exponential form, you have the base, you're putting in a power, and you're asking, what is that equal to? What is the number you get when you raise the base to that power? In the log form, you have a base, you're given a number, and you're asked for the power. So these two functions, the exponential function, f of x equals, say, 2 to the x, is the kind of function where you put in, for your domain, you're putting in exponents. And for your range, you're getting out numbers. And when I say numbers, I mean like in this equation. And then in the logarithmic function, you would have something like g to the x equals, you'd have log, say, base 2 of x. And so your domain in the logarithmic function, you're putting in x's, and those are numbers. And you're getting out exponents. So these two functions are inverses of each other. Their domains and ranges are flipped. So the reason there's this logarithmic form, the reason there's a logarithmic function, is because you're asking a different question. In the exponential function, you're asking, what do you get when you put this exponent on the base? In the logarithmic function, you're looking for exponents. So you put in a value and you say, how would I get that by putting an exponent on 2? What exponent would I put on 2 to get that x? So you're asking, in one, you're asking for a number. In the other, you're asking for an exponent. So as I said, the inverse function of the exponential function is the logarithmic function. So let's see if we can find the logarithmic function from the exponential function. So we have the exponential function here. Let's see if we can find its inverse. So when we try to find the inverse of a function, first of all, we change f of x to y. And then we swap the x and the y. So we'll have an x equals b to the y. And then we're supposed to isolate y. But we don't have a method for isolating y in this situation, where y is the exponent. There's really nothing we can do to get y by itself at this point. So first of all, to figure that out, we'll figure out the definition of a logarithmic function. So if x and b are positive real numbers such that b is not 1, then y equals log base b of x is called the logarithmic function base b, where y equals log base b of x is equivalent to b to the y equals x, which is what I just said on the previous slide. The expression log base b of x means the exponent you put on b to get x. So log base b of x equals the exponent you put on b to get x. So the terminology we really use in the logarithmic form is the little number next to log is the base. The number that's next to the log is called the argument, just like if you had sine theta, theta would be the argument of the function. And then the number that is the exponent that you would put on 5 to get 125 is the logarithm. Log base 5 of 125 equals 3. It equals that logarithm. So logarithm, as I said before, is an exponent. Okay, so now we can show that the logarithmic function is the inverse function of the exponential function, because if we have f of x equals b to the x power, and we change that to y equals b to the x, and then we swap the x and the y, now we know how to get the y by itself. We can just take the log base b on both sides. So log base b of x is equal to log base b of b to the y, and the exponent you put on b to get b to the y is y. That's what log means. The exponent you put on the base b to get b to the y. B to the y is your argument. So the exponent you would put on b to get b to the y is y. So log base b of x equals y. So log base b of x equals y is the inverse function of the exponential function b to the x. All right, so let's write each equation in exponential form. So you've got log base 2 of 16 equals 4. To write that in exponential form, it's going to be base to the power equals the number. When you have log base 10 of 1 over 100 equals negative 2, you write that in exponential form as base to the power equals the number. To change log base 7 of 1 equals 0 into exponential form, you would say base raised to the power equals the number. So the two forms, you just have to get used to where the things go. So the base is the little number there. That's pretty easy. The exponent is on the right side of the equation, and the number is the argument. All right, so here we're going to write each equation in logarithmic form. So we're going to write log, the base here is 3, the number is 81, and the answer is 4. What exponent do you put on 3 to get 81? 4. All right, 10 to the 6th equals 1 million, so we're going to say log base 10 of a million is going to equal 6. What exponent do you put on 10 to get a million? 6. Okay, next one, we've got 1/5 to the negative 1 equals 5. So we'll say log, the base is 1/5, and the number is 5. And the question is, what exponent do you put on 1/5 to get 5? And that is the power, negative 1. So log, base, argument or number, and exponent. Okay, so now we're going to talk about the equivalence property of exponential expressions, which will help us find logs without using a calculator. For the logs that are pretty simple that we can actually figure out without a calculator. So if b, x, and y are real numbers with b greater than 0 and b not equal to 1, then b to the x equals b to the y implies that x equals y. So if you have something like 2 to the x equals 2 to the y, if the bases are the same and they are equal to each other, then the exponents must be the same. There would be no way to have 2 to the something power equal 2 to the something else power. That wouldn't happen. So x and y have to be equal if the bases are equal. So we're going to use that fact, that property of exponential expressions to figure out what these logarithms are. So we're going to evaluate the expression. So on part A, you've got log base 4 of 16. What does that mean? what is that information that you will get by taking log base 4 of 16? You're looking for an exponent, right? You're looking for what exponent would you put on 4 to get 16. All right, well, we know we could write this 4 to the x, whatever. We don't know what it is. We're going to figure it out. But thankfully, we can write 16 as a power of 4. So 16 is equal to 4 squared. We know that. Therefore, if 4 to the x equals 4 squared, then x must be 2. So the exponent you put on 4 to get 16 is 2. And you probably knew that already. So some of these are going to be really simple. Some of them you may have to think about it a little bit before you can figure it out. All right, log base 2 of 8, that is asking the question, 2 to the what power is equal to 8? Well, we can write 8 as a power of 2, so 2 to the x. 8 can be written as 2 to the third, so we know that x must equal 3. Log base 1/2 of 8, that is asking you the question, what exponent would you put on 1/2 to get 8? Well, we know that 8 can be written as 2 to the third, so we could have 1/2 to the x power equals 2 to the third. And now the bases are not exactly the same, but if you flip the base on the left side and give it a negative exponent, then the bases will be the same. So you could say 1/2 is the same thing as 2 to the negative 1 power, and you're raising that to the x power, and you're getting 2 to the third. And you know that if you raise a power to another power, you can multiply those exponents. So you've got 2 to the negative x equals 2 to the third. And so since those bases are the same, the exponents must be the same. So negative x must equal 3, which means x would be negative 3. And that's definitely true. If you put negative 3 as the exponent on 1/2, you will get 8 because that would be 2 to the third, which would be 8. Okay, so logarithms with base 10 are called common logs because that is the most commonly used kind of log, a log base 10. We often want to find how to write a number as 10 to a power. So the logarithms base 10 are called common logs. And on your calculator, the button you would use for that is log. Logarithms with base e are called natural logs. And that is another kind of log that we use a lot because that has to do with compound interest and lots of financial things. So the calculator button for the natural log is ln. All right, so we're going to evaluate these logarithms here without using a calculator. So log with no base on it means log base 10. So for this, we're trying to find out 10 as the base to what power will give you 100,000. And so we would have 10 to the x equals 10 to the fifth, and therefore x must be 5. Log of 0.001 in that problem, when you have a log with no base, that means 10 to the what power is going to give me 0.001. Well, 0.001 can be written as 10 to the negative 3, and so x must be negative 3. Natural log of e to the fourth, that says what exponent would you put on e to get e to the fourth? Well, clearly that is going to be 4. And here on D, that question is what exponent would you put on e to get 1 over e? Well, 1 over e can be written as e to the negative 1, so x must be negative 1. If the bases are the same, the exponents must be the same. All right, now we're going to approximate logs using a calculator. So on your calculator for log 5,809, you would just punch in 5,809 and hit the log button. And if you do that, you will get about 3.7641, and that is just an approximation. And so that would be the exponent, or close to it, that you would put on 10 to get 5,809. All right, on the next one, you've got log of 4.6 times 10 to the 7th, and you are going to figure out what exponent do you put on 10 to get 4.6 times 10 to the 7th. So you're going to punch that into your calculator, and to do that, you're going to hit 4.6, and then you want to multiply that by 10 to the 7th. You want to write this in scientific notation. To do that on your calculator, you would hit the EE button, and that will let you put in the exponent on 10, which is 7. So if you do that, you're going to have 4.6 times 10 to the 7th power, and then you're going to hit log. And when you do that, you will get about 7.6628. Log base 10 of 0.003. Again, you're just going to punch that into your calculator, 0.003, and hit the log button, and you can get about negative 2.5229. Okay, and before I move on, let's just think about, could we estimate these values just in case maybe we punched it in wrong? It's a good idea to kind of think about what should I expect the answer to be. So, for example, for log of 5,809, you're asking the question, what power do you put on 10 to get 5,809? Well, I can get a little bit of an estimate because I know that if I put a power of 4 on 10, so 10 to the 4th is 10,000. And if I put a power of 3 on 10, I'm going to get 1,000. So I know that the answer has to be somewhere between 3 and 4 for the exponent on 10, because 5,809 is between 1,000 and 10,000. So the exponent that you put on 10 to get 5,809 is going to be somewhere between 3 and 4, because 5,809 is between 1,000 and 10,000. And we did get an answer that was between 3 and 4. So you can do that for any kind of problem like this. So for part C, I can do the same thing. I can say, all right, I've got 0.003. I know that 10 to the negative 2 power is 0.01, and I know that 10 to the negative 3 power is 0.001. And of course, 0.003 is between those two values. So I know my answer must need to be between negative 2 and negative 3. So it's a good idea to kind of do that estimate before you just punch it into your calculator. All right, for natural log of 472, you just punch it in, 472, hit the LN button, and you're going to get about 6.157. And then for natural log of 0.05, just hit 0.05 and then hit LN. And you're going to get about negative 2.9957. And then natural log of the square root of 87. You're going to hit 87. Then you're going to hit your square root button. And then you're going to hit natural log. And you're going to get about 2.232. So now we're going to look at some properties of logarithms. These things are always true. Number one, log base b of 1 is always 0. No matter what base you have, if you're trying to figure out what exponent you would put on that base to get 1, it'll always be 0. b to the 0 is 1. So for example, log base 5 of 1 equals 0 because 5 to the 0 is 1. All right, number 2, log base b of b is always going to be 1 because b to the 1 is always b. Therefore, if you have something like log base 3 of 3, you get 1 because what exponent do you put on 3 to get 3? 1. 3 to the first is 3. Part 3, log base b of b to the x is always x because b to the x equals b to the x. That question you're asking there is what exponent do you put on b to get b to the x? Well, x. Because if you're looking at, say, log base 2 of 2 to the x, that equals x because 2 to the x equals 2 to the x. What exponent do you put on 2 to get 2 to the x? X. Number 4, b raised to log base b of x is equal to x because log base b of x is equal to log base b of x. So when you have this exponent here, you're putting the exponent on b. That is the exponent you put on b to get x. Therefore, you get x. I know it's very confusing, but it's also really super obvious. And maybe that's why it's so confusing. Log base 7 of x is the exponent you put on 7 to get x. So if you put that exponent on 7, you get x. Since logarithmic function is the inverse of the exponential function, their graphs are reflections of one another across the line y equals x. So we've talked about the exponential function when you have a base greater than 1, and that is the function that comes in from the left and then shoots up, and it goes through the point 0, 1, because remember, whatever base you have, if you want to get 1, you put the exponent 0 on it. The logarithmic function now is the inverse function. So you flip it over the line y equals x. This line is y equals x because remember, you're flipping the domain and the range. What used to be x's are now y's. What used to be y's are now x's. And so the logarithmic function looks like this, where it's coming up from the bottom and it's shooting off to the right. And it goes through the point 1, 0 instead of the point 0, 1. All right, so if we want to graph these logarithmic functions, we know that it's going to be coming up from the bottom and then shooting off to the right. But we can plug in a few numbers for part A, x and y. If you put in the number 4, let's say, for x, what exponent do you put on 2 to get 4? That would be 2. If you put in, say, 1 for x, what exponent do you put on 2 to get 1? That would be 0. And then log base 2 of 2, what exponent do you put on 2 to get 2? That would be 1. So we could plug in some of those points, 2, 1, and 1, 0, and 4, 2. And if we put in something like 1/2 for x, what exponent would you put on 2 to get 1/2? That would be -1. So at 1/2, you're going to be at -1. So that's going to be coming up from the bottom. And then it is going to shoot off in this direction. All right, for part B, you have log base 1/4 of x. And so you put in some values. So you can put in 1 for x here, and you're still going to get 0 because the exponent you put on 1/4 to get 1 is 0. So we could try 4. What exponent you put on 1/4 to get 4? That's going to be -1. That flips it upside down. We could try 16 for x. What exponent do you put on 1/4 to get 16? That's going to be -2 because 1/4 raised to the -2 power, that means you flip it and raise it to the second power, which is 16. So some of these points, you've got 1, 0, and you've got 4, -1, and then somewhere way over here, you've got -2 for your y. Then we could try for x, we could try 1/4. What power do you put on 1/4 to get 1/4? And that would be 1. So 1/4, 1 is on here. So you know that basically it's going to look like the logarithmic function flipped. And it's going to be going like this. And so if your base is a number greater than 1, your logarithmic function is going to come up from the bottom and shoot off to the right. If your base is between 0 and 1, you're going to come down from the top and shoot off to the right. So for exponential functions, your domain is going to be from -infinity to +infinity because you can cross the y-axis. You can put in 0 for x and you will get a value. The range is only going to go from 0 upward. You can't get 0 by raising b to some power. So the range is going to be from 0 to infinity. The horizontal asymptote is going to be the x-axis, which is y equals 0. It passes through the point 0, 1. If b is greater than 1, the function is increasing. It's going up. If b is between 0 and 1, the function is decreasing. It's coming down. And so for the logarithmic functions, as I said, the domain and range are flipped. For the logarithmic function, the domain, the x's, are only going to be the numbers greater than 0. Everything is to the right of the y-axis. So the domain is going to be from 0 to infinity, and the range is going to be from negative infinity to positive infinity, because it can go all the way up. It can cross the x-axis, go all the way down. So negative infinity to positive infinity is the range for the logarithmic function. The vertical asymptote is going to be the y-axis, which is x equals 0. It passes through the point 1, 0, so other way around from the exponential function. Now, if b is greater than 1, the function is increasing still. It's coming up from the bottom and shooting off to the right, so it's increasing. And if b is between 0 and 1, the function is decreasing. It's coming down and going that way. So to graph a logarithmic function, we could use transformations. So you've got this function, log base 2 of x plus 3 minus 2. So what you could do is go ahead and graph the function log base 2 of x. You could scoot it to the left 3 units, and you could go down 2 units using what we know about translations. So you have some of these points here, and you can go ahead and graph that function. Now you're going to use your translations to make it into this function, log base 2 of x plus 3 minus 2. So you have added 3 to x, which means you scoot the function 3 units to the left, and you are subtracting 2 from the whole function, and that means you're going down 2 spaces. Okay, so we've talked about this already, but when you have the logarithmic function f of x equals log base b of x, the x's you put in have to be positive, because you're looking to raise b to some power to get that number, and there's no power you can raise b to, if b is positive, to a exponent that will give you a negative number. All right, so if we want to find the domain for this function right here, we know that 2x plus 4 has to be greater than 0, and that's really the only thing we have to worry about. Anything you can put in anything as long as the argument is positive, because you can always find an exponent to put on 2 that will give you any number in the universe. So 2x plus 4 has to be greater than 0. So we just solve it. 2x is greater than negative 4, so x is greater than negative 2. This would be the domain for that function, and we would write that as negative 2 to infinity. For part B, g of x equals natural log of 5 minus x, again, all we need to worry about is that the argument is positive, because we can always find an exponent to put on e to get whatever that number is, as long as it's positive. So 5 minus x is greater than 0, which means that 5 is greater than x. In other words, x is less than 5. So we have negative infinity up to 5 for the domain. So part C is a little bit trickier, because you have to look at a couple of situations. So the argument here, we're going to factor it, x plus 3, x minus 3. And so in this case, we have to say that x plus 3 times x minus 3 is greater than 0. What will make this greater than 0? Well, either they both have to be negative or they both have to be positive. So x plus 3 is greater than 0 when x is greater than negative 3. X minus 3 is greater than 0 when x is greater than 3. So both positive, x has to be greater than negative 3 and greater than 3. Well, when does that happen? That happens when x is greater than 3. Because if it's greater than 3, it's greater than both. So x has to be greater than 3 for that to happen. And then when are they both negative? All right, well, x plus 3 is less than 0. X minus 3 is less than 0. That happens when x is less than negative 3, or x is less than 3. And so when are both of these things true at the same time? Well, if x is less than negative 3, it's certainly less than 3. So it has to be this. So the domain for this function is going to be the numbers greater than 3 and the numbers less than -3, because those are the only way to make either both of them positive or both of them negative. Anywhere in between -3 and 3, you're going to get a positive and a negative, so that's not going to work. All right, so we would write that as -infinity up to -3 union 3 to infinity. Okay, so now we're going to look at a application of logarithms. So the intensity I of an earthquake is measured by a seismograph, a device that measures amplitudes of shock waves. I sub 0 is a minimum reference intensity of zero-level earthquake against which the intensities of other earthquakes may be compared. The magnitude m of an earthquake of intensity I is given by m equals log, the common log, of I over I sub 0. So we're going to determine the magnitude of the earthquake that devastated Haiti on January 12, 2010, if the intensity was approximately 10 to the 7.0 times I sub 0. So they say that the intensity, which is I, is 10.70 times I sub 0. So that's my numerator, 10 to the 7.0 times I sub 0. And then the denominator is just I sub 0. So the I sub 0's cancel, and we have m equals log base 10 of 10 to the 7.0, right? Because log with no number next to it is a common log. So if I have log base 10 of 10 raised to the 7.0, using the properties of logs, I know that that is 7.0. If the base is 10 and I'm asking what exponent do you put on 10 to get 10 to the 7.0, then that would be 7.0. So that would be the magnitude of that earthquake. Part B says determine the magnitude of the earthquake that occurred near Washington, D.C. on August 23, 2011, if the intensity was approximately 10 to the 5.8 times I sub 0. So m equals log, common log, of I over I sub 0. So I, the intensity, was approximately 10 to the 5.8 times I sub 0. So that goes in the numerator, 10 to the 5.8 times I sub 0 over I sub 0. And so that will just be log of 10 to the 5.8. And we have the same situation as before. What power do you put on 10 to get 10 to the 5.8? That is 5.8. Part C, how many times more intense was the earthquake that hit Haiti than the earthquake that hit Washington, D.C., round to the nearest whole unit? So you're looking for how many times more powerful was this earthquake than that earthquake. So you're going to ask 5.8 times x is 7.0. And so to solve for that, you would say x equals 7.0 over 5.8, and you would punch that into your calculator, and that is about 1.21 times as powerful. And what I did want to say also is that you can go ahead and scan in your test with this homework. You can just scan in the test and turn it in